So continuing on with our trigonometric identities and formulae, we're going to look at double angle formulae. Extra points for anyone who gets this joke. Okay, so double angle formulae is finding the ratio when you double the angle, as the name would suggest. So doubling the angle means instead of theta, we're looking at sine 2 theta. And there's a range of formulae for, again, for sine, cos and tan that we can use. And when you get fluent with them, you can start using them to rearrange formulae into something that's a little more wieldy, and do some simplifying and also proving, doing trigonometric proofs. So for sine, our double angle formula is simply that sine 2u is equal to 2 sine u cos u. Now, for the addition formula, I didn't show you the proof, but for this one, it's pretty straightforward using the addition formula, so I will run through it. Okay, so 2u is obviously just u plus u. So we can say, well, that's sine u plus u. Now, using our addition formula from the previous video, we know that that's going to be sine u cos u plus cos u sine u. Oops. And of course, because these are the same, they're similar terms or like terms, so you just get 2 sine u cos u. Okay, so reasonably straightforward there. For cosine, there's actually 3. So this is the main one, but then using Pythagorean identity, remember that cos squared u plus sine squared u equals 1. You can then rearrange this and get it just in terms of cos or just in terms of sine, which sometimes can come in handy as well. So again, we're using our double angle formula, so we're saying cos of u plus u. Okay, and if we do that, we get cos u. So cos u minus sine u, okay, which is our cos squared u minus sine squared u. Okay, so not to be mixed up with cos squared u plus sine squared u, which is different. That's Pythagoras. Okay, and then yeah, if you rearrange this, so you rearrange this the Pythagorean identity here, you get sine squared u is 1 minus cos squared u, and then if you substitute that into here, that's how you do these. So there's actually 3 for cos 2u, and you pick whichever one you want to in terms of. So if you're just looking for cos, use that one. If you're just looking for sine, use that one. If it doesn't matter, you're happy to have both, use that one. It'll make a little bit more sense as we sort of come into doing some proofs and some solving. And the last one, we're doing the same thing again, tan u plus u. Okay, and that's just tan u plus tan u over 1 minus tan u times tan u times tan u, and that's where you get your 2 tan u over 1 minus tan squared u. Okay, so pretty straightforward, nothing too complicated there. So let's have a look at a couple of examples, how we actually use these things. Okay, so the first question says if tan theta is 4 on 3, and you know that theta is between 0 and pi on 2, or 90, so we're talking first quadrant of the unit circle. So quick sketch. Okay, do a sketch, makes me happy. So somewhere in here, evaluate sine 2 theta and tan 2 theta. Okay, so it would be easy first to look at this if we draw a right angle triangle. And the clue here is 4 on 3. Okay, we have theta. We know that that's going to be 4 over 3, opposite over adjacent. Now this is a 3, 4, 5 triangle, so we can fill that in, okay, just from our knowledge of Pythagorean triads. If we then want to find out what that is, we're looking at sine, sorry, we've got sine 2 theta, and we know that that's 2 sine theta cos theta. Okay, now we need to know what is sine theta and cos theta. From up here, we can work out straight away that sine theta is 4 on 5, cos theta is 3 on 5. Okay, so this is just going to be 2 times 4 on 5 times 3 on 5, and that gives you 24 over 25. Okay, so look for things, if you have ratios of like 3 over 4 or 4 over 3 or 5 over 3, anything to do with 3, 4 and 5, that's a bit of a clue here that you might be dealing with a 3, 4, 5 triangle. Okay, now for B, we want tan 2 theta, and we know that the identity for that is 2 tan theta over 1 minus tan squared theta. Okay, so replacing tan theta with 4 on 3, we get 2 times 4 on 3 over 1 minus, now we're squaring that, 16 on 9. Okay, and if you work all that out, what you end up with is minus 24 over 7. So a little bit of fraction manipulation and juggling there, but that's what you should come out with there. Second example here, it says if we've got sine 2a is m and cos a is n, then what is tan a? Okay, so what we probably want to look at first is, well, we know that sine 2a, that's m, so m equals 2 sine a cos a. Alright, we also know that cos a is n, so we can say m is equal to 2 sine a times n. Okay, that hasn't really got us all that far. We haven't said anything about tan yet. Luckily we know that tan is sine or cos. Tan a equals sine a over cos a. Okay, again we know this is n. Sine a over n. Because we know that the answer can't have a sine or cos in it, so we're trying to get rid of these. We can also, from over here, we can write sine a in terms of m and n. It's going to be m over 2n. So far so good. Okay, so now we can say, well, that's m over 2n, all divided by n. Okay, which gives us m over 2n squared. Having done that, is that in the answers? Yes, it is. It's answer number, or option A. Okay, so this is a little bit of a beginning into a sort of trig proofs kind of question, where you're given some information and told kind of what you need to find, but you're not really sure where you're going. So with all of these, what I would recommend is just make a start. Make a start anywhere. If it looks like you're diverging away from where you need to be, so if you start doing something and you end up with cos squareds and sine squareds and you know that you need to have an answer that doesn't have a cos or a sine in it at all, then you might be going in the wrong direction. You can always pull it back and start again. But if you just sit there staring at a blank page, the answer is not usually likely to leap out and bite you on the nose. So you do really need to start somewhere and give it a go. So in summary, again, don't need to memorize them, but you need to know how to use them. This is the beginning of trigonometric proofs. There is a knack to it. It really gets easier as you get more practice. You get used to little tricks and hints in the questions and ways of approaching them to get to the way to the answer you're looking for. I like to sort of compare them with those choose your own adventure books where you get to the end of a chapter and you have an option. And if you take one option, then you solve the mystery and you become a hero. And if you choose the other option, then you end up coming to a sticky end and no one ever hears from you again. They're a little bit like that. If you do choose the wrong way, you'll end up with a very complicated, sort of messy formula that either proves itself or says something really useful like 1 equals 1, or just gets so unbelievably complicated that you can't see your way out of simplifying it. And then when you pick the right way of doing it, or one of the right ways, because there's usually several approaches, it'll all come out neatly in the wash, as we say, and cancel down and you'll get where you're going. So if you do think that you're tying yourself in knots, just stop, go back, maybe try something else. Because as I said, as we give you more formulae, so far we've only got the addition and the double angle formulae, and the Pythagorean identity. As you get more sort of relationships between all those things, you need to get quite adept at working out which one it is that you need to use to get the answer that you're after. Okay, so it's okay to start the question even if you don't really know where it's going. Just try something. It's better than sitting there going, I don't know.